me again. On Monday, I spent an hour motivating, introducing the ZX calculus, and introducing a lot of graphical techniques and rules along the way. Particularly multicolored spiders, decorated with phases, and several kinds of diagram rules. We have these fusion rules. We had some rules coming from strong complementarity, these kinds of rules, and rules coming from the block sphere. So on Monday, I gave everything really without much motivation. So I gave some hints at some of the applications that we would get into. But really, it's today that's all about applications. I'm going to talk about 4 areas where this stuff's been applied. Some of the stuff we know there, some of the stuff you can show and do, and some of the stuff we don't know, or that isn't quite beautiful yet. Yeah, ZX calculus. Today we'll see how to use it. Alright, so this first area I'm going to talk about is quantum algorithms. And a lot of this point of view on quantum algorithms comes from this paper by that guy. And it's really a graphical approach on quantum algorithms. As most of you must know, a lot of the standard quantum algorithms follow a similar recipe. You take some classical function, which you want to know something about, that you want to do something quantum to, and you lift that up and you make a quantum oracle. And then you prepare some sort of superposition of an input, you measure the outcome, and you get something good out of it. Right? So most of the standard algorithms look like that somehow. So before we talk about how you can build an oracle, we'll talk about what classical functions look like in this graphical language. So we've already defined arbitrary quantum maps, but not all of these will necessarily correspond to a classical function that's been lifted to a quantum map. But it's really these that do. And this is kind of the most simple way you could imagine lifting to a quantum map. I just take some function f, which goes from some finite set to some other finite set, and I just lift that function to basis elements. Right? So I apply to a basis point I, and I get another basis point, which I've just labeled f of I. Rather than doing it this way, which is kind of fiddly and points based, you can actually do this with a diagram equation. Well, actually 3 diagram equations. These equations totally characterize what it means to be a classical function. So we say that a quantum map encodes a classical function from this basis to that basis. So you have to say what these are, because you have to say which bases I've encoded the function relative to. From here to here, if these 3 equations are satisfied. And they all kind of make intuitive sense. If you think of this thing as a copy, you think of this thing as a delete. Maybe this one a bit less so. So here, if I put in my classical input, and I copy the output, and that's the same as if I copy my classical input and I do f to each of them. And similarly here, if I put in my classical input and I delete it, that's the same as just deleting my classical output, right? So this looks very similar to causality for classical maps, but you notice these are all quantum, right? So it's a slightly different thing. And here this just says it's well behaved with respect to how I might want to transpose this thing using these various basis structures. Right, so here's how you can prove that theorem on the previous slide. It's very easy, it just has to do with evaluating on points. The only kind of non-trivial part is that, well, here when we're saying that satisfying these diagram equations implies encoding a classical function. Well, first we show that f of I is copied by Gray. And then it's a property of these dots, of all these dots, that the only things that these dots copy are basis elements. So that's one of the important facts about these spiders, which can be used to totally characterize them. So in fact, since the only thing copied by gray is a basis element, then f of I has to be a basis element. So that's how you prove the converse there. So now, unless f is a bijection between two different bases, this thing is not going to be unitary in general. It's a function, so it throws away some information. But in quantum computing, there's a standard trick for patching this thing up to actually get a unitary. And you'll see this kind of in standard textbooks, where I just introduce some ancilla there, and I keep my input, but I also XOR my output with my ancilla. And it just happens to be that this, well, fairly easy to argue that that's always a unitary. We can do the same trick graphically. And in fact, we don't even really have to say XOR. It'll suffice to have unbiasedness. But here, we're copying the input, right? We're keeping one copy aside, and we're applying one copy to F. And then we're doing something with the ancilla in our output. And then, whenever white and gray are complementary spiders, we just have a diagrammatic proof that this thing, composed with its adjoint, equals this, that's just by the spider rules, equals that. Here I've sort of squashed those two gray dots together there, you see what's happening. F has come up, sort of been transposed. I pull it through like that, and this is where complementarity plays a role, right? So we have a pair of edges there, connecting two different color spiders, and they just fall away. And then the whole thing goes away, right? So we have a totally diagrammatic proof that this gives us a good oracle. The other direction looks a lot like that. If I compose U dagger rather than U dagger U. And in fact, this property of constructing an oracle totally gives us a way to characterize complementarity as well, which is something that's both directions are discussed in this paper, which is coming up in QPL and probably available somewhere soon. So keep an eye out for that. So now we know how to build an oracle. Let's have a look at the Deutsch-Jose algorithm. So given a function, right, I'm just going to use bits here, but if I just change this white to some other color, red or something, I could do it with a bigger set. But I'll just keep things simple and use bits. Right? Is it constant? Right? This one obviously means constant. I'm just deleting the input and putting out some constant value as my output. Or is it balanced? Now, while this one is kind of obvious, that's, well, it needs to be justified a bit. So the reason that second equation means balance, well, let's just unfold it a bit. So here I'm working in single, but if I prove a single equation, it holds in double command. Right? So if I look at this thing, well, I can unfold that white dot as a sum. Right? It's a spider. It's a sum over all those basis elements. And then I can split that sum into two halves. Right? It's the half where f of I equals 0, in which case that I is going to go through the f map and make a 0. And similarly for f of I equals 1. Right? Now, oh no, that's correct. Right, so now if you look at how this pi dot is defined, that actually equals 0 plus e to the I pi 1, right? Which this thing is minus 1. So when a 0 hits that pi, it's going to make a plus 1, right? And when a 1 hits this pi, it's going to make a minus 1. Alright, so I can reduce that. And I get a bunch of 1s and a bunch of minus 1s. Of course, if I have the same number of each, these are going to cancel and that's going to go to 0. So that's why that equation means balanced, right? So now we have a nice graphical way to say either. So we can describe Deutsch-Jose this way. Right? We prepare some stuff in X. We apply our oracle and we measure again in X. right? It's about as simple of a quantum algorithm as you can come up with. Right? So we do a bit of simplification, right? So here we prepared a 0 and a 1. Now a gray 0 is a white dot. A gray 1 is a white pie. Those were some things I discussed on Monday, but don't worry if you didn't remember that fact. Then these simplify, right? The pie comes up here and copies. This goes there and makes a cup. And we get something that looks like this, right? Now if f is constant, then we can simplify it a bit more, right? Because I can replace f here with its constant expression, right? Delete and then put out an I. So that part's just going to vanish. That's going to go there. White dot is gray triangle. 0, 1, right? So the thing we're getting out at the top is a probability distribution of outcomes. And it turns out that it's deterministic, right? The only outcome we'll get is 0, 1. So we get 0, 1 with certainty. So if we look at the balance case, we can look at the probability that we'll get this same outcome 0, 1 just by taking the inner product here, right? So it comes down, makes a gray dot, or makes a gray triangle, white dot, comes around, balance, that equals 0. So 0, 1 never happens. Okay? So that's stoichiosa, right? In the case where it's constant, we'll get 0, 1. In the case where it's balanced, we'll get anything else, we'll never get 0, 1. So similar things can be done for a single-shot version of Grover's algorithm. So this is where you have 1 in 4 elements are your marked elements, right? The way you get full Grover is you iterate this to kind of decrease the number of elements you have to have marked, right? So the single-shot version works, and there should be some way to generalize that. And also the hidden subgroup problems. And the interesting part is all of these pictures look almost exactly the same. I mean, these are pictures out of this paper by Jamie, so the notation looks a bit different. But here is basically that Deutschiosa I just described to you. And the other two, well, look quite a lot like that. I mean, the algorithms look quite similar. But it makes it kind of blindingly obvious when you use this pictorial form. So the next thing I'm going to talk about, well, that was just kind of a hint of algorithms. The algorithms is kind of the newest thing, so we'll see what comes out of that. The next thing I'm going to talk about is measurement-based quantum computing, or MBQC. Now, probably quite a lot of you are already familiar with the idea here. But MBQC, which some people call one-way quantum computing, is an alternative universal paradigm to the circuit model. And the idea is rather than repeatedly applying some operations to a small number of qubits, I start with a big resource state, which is in some known state, and I start doing measurements locally to different points on this big entangled state, right? And I'm getting outcomes as I go, and maybe making different measurement choices as I go. But crucially, we can choose our later measurements based on the outcomes we got in the past, right? And that's kind of where all the quantum speed-up comes from. That's where the universality comes from. So if it weren't for this feed-forward thing, you would have just kind of a fancy random number generator. But this is, so that's how quantum MBQC works. And we can actually picture this in the ZX calculus. Quite elegantly. So first I'll make a little abbreviation here that rather than having this big chunky thing for Hadamard's, there's going to be a lot of Hadamard's around, so I'll just draw them as a little square like that. And it doesn't matter which way we draw it because it's self-transposed and everything. So this thing here actually encodes a controlled Z operation. So I showed you on Monday how you can build a controlled knot. You can argue very, very similarly to that that's in fact a controlled Z. And then these things all commute with each other. You can see why it's just spider fusion, right? Here's a white spider and here's a white spider, so I can quite easily just slide these bits of the diagram past each other. So the order that I do these things doesn't matter. And in fact, I can just squash them all. And the only thing that I'm left with are the edges. Right? And then the important part about this state that I've prepared is its graph, is its underlying graph. And you can see immediately there's this bijection between a certain family of ZX diagrams and graph states that people talk about in DQC. Right? So anytime I take a graph state, I just immediately know how to draw the similar NDQC diagram. I just put whites with a single sort of output edge on them, and then I put edges with a Hadamard every time I see edges over there. Right? And for certain kinds of these, I can even simplify more, because these Hadamards are color changers. I can just pull them out with some local operations, right? And then I can just see that this kind of graph state, or this thing is called a cluster state actually, it's just an alternating grid of two different colors. So it gives you a very nice kind of starting point for working with these kinds of algorithms. So that's how you prepare graph states. The kinds of measurements you do are all of this form. So that's a basis measurement right there. It's got two basis elements. It's got alpha, an alpha phase, and an alpha plus pi phase. Right? So these are 180 degrees away from each other. They form a orthonormal basis. Right? And it's really picking these alphas, which is like my programming language. Right? It's choosing my measurement angles is choosing which program I'm performing in NDDC. So, the sense in which the choice of measurements is actually doing something is that if I choose a measurement alpha, that's going to stick an alpha phase on that point in the graph, right? Well, if I get the outcome alpha plus 0 pi, so if I get the outcome alpha, that'll stick an alpha phase right there. If I get alpha plus pi, I get the thing I wanted plus an error. So the point of NDQC is that you can sort of feed forward these errors, and you can correct them as you go. Right? And you can see this very easily. It's kind of obvious how to do this in the ZX calculus. Here my pi error comes down through here, moves through this Hadamard K, gets copied, so it comes out here, goes through another Hadamard K, it comes out there, right? And none of the rest of my global state is affected. And this particular setup is good because it has this property that errors only really affect kind of the neighborhood of something. So I can kind of, in a finite number of steps, I can always correct any measurement errors I've made. And by correct, I mean that later, when I'm choosing new measurement choices, I'm going to account for the fact that I had an error here, right? So since I've fed forward these errors, I'm going to decide to measure, instead of measuring beta and gamma, I'm going to measure minus beta and gamma plus pi, right? Because when this thing hits that thing, well, that's the pi flip rule from ZX calculus. That's just going to flip the sign of the beta, and that pi is going to go away. And then these two pi's are going to add to each other and cancel, right? Of course, these things might introduce errors, which you'll then sort of correct onward. But that's how it works. That's how you build up a deterministic circuit just by doing measurements. So your choice of angles is kind of one half of what it takes to write an NDQC program. The other half is deciding which kinds of feed forward you're going to do. So what later bit am I going to condition on which outcomes that happened earlier? Right? And there's quite a nice way to do this called the Conditionals ZX calculus, where we replace our phases with a phase that's just got this extra little Boolean flag which says if it's 0, do this, and if it's 1, do that. Right? It's just like it's like a classical wire coming on. It's just with these things we don't want to be putting classical wires everywhere. It's very messy. So for instance, I can pair up this measurement I'm doing here. So that's a measurement of alpha, right? And that's my possible error, with its associated correction. Okay? So this gives us a totally graphical way that I can write MDQC programs. I can write all my angles, and I can write all my corrections right there in the notation. And we can also beef up the ZX calculus a bit and just have all these conditionalized versions of the rules. And this gives us a totally graphical way of reasoning about what an MDQC program is going to do. Right? So, in particular, you can very quickly prove that MDQC is universal just by writing a few simple patterns like this and proving that they're equivalent to various circuits, right, to a generating set of gates. So that's like a one-page proof. We have a class here called Categorical Quantum Mechanics, and one of the lab exercises that they do is to prove this using quantum math. So that's quite a nice thing you can. So this is more of a survey talk. So at this point, I'm just going to cite a whole bunch of stuff and say, go read this. There's lots of goodies. So there's a lot of relationships going back and forth between ZX and MDQC because they're so closely related. In particular, this Euler decomposition rule, the fact that I can take my Hadamard, my color changer rule, and decompose it as pi on 2s in a certain way, is equivalent, in the presence of all the other rules, to local complementation. Local complementation is something that the MDQC people use a lot for transforming graph states into other kinds, and proving various kinds of things. So that was proved by Ross and Simone, one of the first papers relating these two kind of approaches. And this is actually the fact that was used by Miriam to prove completeness for ZX calculus. So this is an example of taking something from MDQC and importing it to ZX land and proving something quite powerful. In the other direction, Duncan and Peredri, the people that wrote the first paper, used the ZX calculus to offer a new technique for transforming certain MDQC measurement patterns to circuits. So a lot of times you want to write a pattern and see that it's equivalent to some circuit, right? The pattern is the thing you implement, the circuit is the thing that you really wanted to do with your quantum computer, right? And they proved that for a certain family of MDQC patterns, where the underlying graph satisfies this condition called generalized flow, which is something from 2007 or so. This was Simone, Elham Geshefi, and some other people came up with this condition. They offer a new technique for turning these kinds of graphs into circuits. And their method, there were some other techniques known, but this was one of the best methods at the time because it didn't introduce ancilla qubits and had some various other nice properties. Also, there's something I've only noticed fairly recently, that Ross has written this quite long and self-contained intro to all of this stuff, which you can get on the archive. It's called A Graphical Approach to Measurement-Based Quantum Computing. So that's probably a good place to start. So the next thing I'm going to talk about is protocols, particularly some security protocols. So on Monday I talked briefly about BB84. So I'll look at that a little bit more now. So most of you probably know how BB84 works, the first quantum cryptography protocol. Should be Alice. Well, no. I prepare something and in one of two bases and encode that as a quantum state and send it to Bob. If Bob chooses the correct measurement, he gets the bit that I sent him, and if he chooses the wrong one, he gets nothing, he gets noise. And then later we, didn't quite want that in. later Bob says, okay, I've measured everything, and then we talk and we decide which bits to keep, which ones he made the kind of correct choices on. Now, if we look at the cases where we both make the same choice, you can argue that with some probability you'll always see the effect of an eavesdropper. And it's, well, the clearest case to see is where the eavesdropper is using the same kinds of measurements as Alex and Bob are, right? So the eavesdropper can't know what I'm preparing. Well, sometimes Eve will get lucky and we won't notice any difference. And you see what happens is my bit actually just gets copied to Eve and Bob. But other times she'll inevitably choose wrong and Bob will get noise. And since we didn't expect to get noise, we'll notice. And then, of course, you make more sophisticated arguments to allow Eve to do more and more insidious things than just measure the same bases as us. But probably the more interesting thing to say is, at least from this graphical point of view, is comparing BB84 to Eckert 91, which is the version of quantum crypto which uses a Bell state instead of a quantum channel. Right? And the only difference is that that one should have been E91 one. The only difference is that we bend this quantum wire here. So this is what BB84 looks like. I send on a quantum channel, and that wire goes away if we make different choices. E91, we start with a shared Bell pair, and when we make the same choice, we get a perfectly correlated classical correlated state, and if we make different choices, we get a totally uncorrelated state. Right? So the reason E91 works is identical to the reason that BB84 works. And it's very easy to see in this graphical language. So Bob, along with 3 Longs and a Zhang, covered QKD in a lot of detail. Recent paper. This picture relating E91 and BB84, at least using quantum classical maps, comes from this paper by Bob and Simon Peregrine, which Chris also mentioned yesterday. It's the one that has to do with this axiomatizing the environments of throwing things away. CDM. A master's student called Anne Hillebrand gave proofs of lots and lots of security protocols in this graphical way. And Vladimir, who is probably here, yeah, he's there in the back, used this double single picture to study what was quantum secret sharing, various quantum secret sharing protocols. So here, the general setup is that we have some GHZ state, which is shared from everybody, between everybody. And they all make some measurements and do a bit of post-processing. And if we all cooperate, you can prove that we can recover the secret. But if they don't, you get noise, so you get the sort of maximally mixed stuff coming out of the end. And you can do all this stuff totally graphically as well. Right, so the fourth and final kind of application area that I want to give you a bit of a taster of is quantum nonlocality. So, John's already been talking about this quite a bit for the last couple of days. Suppose we have some kind of setup like this, where we have maybe some common past, and we have different distant observers, or at least observers that can't communicate to each other. And they're making some measurement choices, and they're observing various outcomes. Now, it could be the case that any correlations that they observe when they make these measurements are due to the fact that they just have some shared classical resource, right? So that there's no kind of strange action at a distance happening. It's all classical correlations. And when we have correlations like this means there's a local hidden variable model for correlations seen. So a non-locality argument shows that the predictions of quantum theory are inconsistent with the local hidden variable model. And they come in two flavors. You have this possibilistic, this probabilistic flavor, which is the Bell style, where you violate some sort of inequality. You also have what are called possibilistic non-locality arguments. So this is like Hardy paradox, or what I'm going to talk about is the GHZ paradox. And these split into two sort of subcategories. You have strong and weak. So weak means that there's no classical thing that exactly reproduces the support of a quantum correlation. And strong means that our quantum correlation is so weird that there's no classical distribution whose support even lives inside of the support of my quantum correlations. So, and it's the strong ones that I'm going to talk about. So we'll look at this possibilistic argument given by GHZ originally, and then it was simplified a bit by Merman. The setup is a single source of particles, and you have three different parties, and they can choose to measure either in X or Y. And we can prove that this thing doesn't support a local hidden variable model. And in fact, rather than looking at all 8 possible configurations here, it suffices to look at just these 4. So what these 4 have in common is there's always an even number of y's, right? So that'll play a role. So we can picture our 2 measurements this way. So what you'll notice is that rather than using 2 different colored dots for my measurements, for my y measurement I'm just doing a rotation by a quarter turn and then doing a normal x measurement. So that's just another way to picture a y measurement. So of course when alpha here is 0, we're doing an x measurement. When alpha here is pi on 2, we're doing a y measurement. So our Merman setup is, I take a GHZ state, which is actually just a quantum spider of this shape, and I do either an x or y measurement to each of these output legs, each of these particles. Then I can reduce that using some ZX rules. So here all the phases come together and they just add up, so that's like spider fusion. I can pull this phase out the bottom to make a phase state. And then I can take this measurement and I can push it through the quantum dot. And that's just strong complementarity here. This step is strong complementarity. So we can represent our quantum correlations in a very nice form. And something that this form makes obvious is that our correlations here have totally forgotten who chose what measurements. Right? So all this phase information, all this what looks like quantum information has just come down here and gotten all shaken up together, and it just doesn't matter where it was. And that's, I think intuitively, that's what makes this argument tick. So these are the 4 probability distributions that are predicted by quantum theory. Right? So in the case where I've got no y's, here I'll get 0. Right? Because if I sum up all of these zeros, I'll get 0. Right? When I have 2 y's, then that'll contribute a pi on 2 exactly twice, so I'll get pi. Now of course it doesn't matter what order my 2 y's are, I get pi, pi, pi. Right? So this is just a picture of what those probability distributions look like. And I can simplify it a bit because white circles are gray triangles. So we've written down what the quantum correlations look like. A generic local hidden variable model for this kind of setup looks like this. So if we have local hidden variables, we can assume already that the 3 particles, as they're flying to each of these detectors, already knows what it's going to say if you choose to measure x or if you choose to measure y, right? So it's convenient to express this thing just as a joint distribution, like this. Right, so this is a probability distribution over basis elements that look like this. So this would be a single basis element in this distribution. So particle 1 is saying that I'll not click if you measure x, and I will click if you measure y. I will click if you measure. See, it says what it's going to say. So we just take a distribution over those. And now we can express the outcomes of all 4 experiments in terms of this distribution lambda. And the way we do this is just by, well, we've got this distribution, we take the probabilities and we copy them kind of into the correct column in our lab book, right? So first, we take the 3 x outcomes, x, 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 right? And we copy it to the first page of our book, which said what we got when we measured x, x, x. And then we take x, y, y, and copy it to the second page. And similarly, yx, y, and yyx, right? So we get something that looks a bit wild in the end, but it's, there's nothing kind of mysterious going on there. So now suppose that the support of this distribution, which we got using quantum theory, contains this classical distribution, right? So that's certainly not going to be true if this thing is strongly non-local. So suppose that's the case. Then we can get a contradiction. The easiest way to do this is making clever use of this parity function. So parity, well, you know what parity is. But the way we can picture the parity function is that, well, we saw on Monday that gray was XOR for white, but everything's totally symmetric in the ZX calculus, right? So white is, of course, XOR for gray as well. So that's how we'll picture the parity function. So first we compute the parities for each of our 4 experiments that we do. And we get something nice happening. The fact that I have this sort of classical split, this classical copy in white, cancels with the parity. And we get this deterministic outcome. And this is why the Merman argument works as well, too, because you don't get deterministic outcomes, but you do get deterministic parities. And that's what this picture is showing. So when we see a 0, that means an even number of detectors clicked. And when we see a 1, this means an odd number of detectors clicked. We can also compute the overall parity. So we're just doing this to be tricky. I mean, somebody, he got a bit clever when he decided to do this. And we see that we get 0, 1. So to summarize what we've done to our quantum correlations, it's this. Right? So we've done the parity of the first 3 and then took the parity of everything else. So we can do the same thing to our classical distribution. So here we've taken this kind of wild-looking thing, which is really just a bunch of classical copies of various kinds. And we take some parities. But the thing that you see happening immediately is that by complementarity, pairs of these legs fall away. Right? So this thing all squeezes together, and I have a pair of legs there, I have a pair of legs there, I have a pair of legs there. And the y's don't contribute at all here to this portion. And then this picture is already symmetric, which is crucial, but it becomes totally obvious that it's symmetric if I just do one more strong complementarity and get this picture. Right? So this probability distribution is symmetric in its 2 outputs. So, when comparing that to the deterministic thing that we got from quantum theory, which is obviously not symmetric, that cannot be in there. Right? So no, I think I can say this. This implies that for any lambda, the support of LHV lambda can't be in the support of this quantum distribution. Right? So that's how the picture of Merman goes. So the kind of question then is where to go, right? And the goal is to be a bit more ambitious. I mean, the most naive way, I kind of think we want to think bigger, like bigger algorithms, more sophisticated protocols, but also to do things in more sophisticated ways, so to get more expressiveness in the diagrammatic language. But at some point we kind of hit a wall in comparison to doing things the kind of standard, Forthcoming style, right? The diagrams get awkward as the size of the problem gets bigger and bigger and bigger. Like, drawing and working by hand with a diagram with 200 nodes in it is quite difficult. Making these slides took a very long time, for instance. But I think the reason there is not fundamental, it's just, it has to do with tooling. So terms and stuff have been around for a long time. As a result, we have a big bag of things to do with them, right? We have variables, and we have induction, and recursion, and indexing, and quantifiers, and all sorts of stuff. So when we meet a new problem, we say, well, I've got this huge bag of tricks, and I'm going to start hitting this problem. And we've also got good tools for communicating about terms and formulas. We have, well, typewriters have been around for a while, but also LaTeX and whatnot. But what about diagrams? Well, the kind of notation we're using really has only been around since the 70s. So making this stuff work better, I think really has a lot to do with coming up with the right tools for working with diagrams. So one thing is you can improve the expressiveness of the notation. Normally when you're proving something, you're proving it for all n, right? Or for all cases of something. We're not just proving that some ground term equals some other ground term. And in fact, we've already got a shadow of this in our language, right? Because our spider rule looks like this. It's an infinite family of rules. And we can actually formalize this. We use this formalism called bang boxes. The bang is kind of like the bang in linear logic. But it really just means that this is now an infinite family of rules, where I'm allowed to repeat what's in these boxes any number of times. Does that make sense? I mean, that's generally how it works. These have a sort of well-defined semantics. And in terms of working with them and communicating with them, I think software tools are the thing that's needed. In particular, what me and a handful of other people have been working on are the quantimatic tools, including quanto-derived, which I'll give a little demo of now. But before I switch to the demo, are there any questions about that stuff? All right, well, let's dig in then. Okay.
I have just an observation.
Yeah.
I mean, although I'm not totally confident with your theory, but an impression. This question of the complexity of diagrams cannot be considered from the point of view of simplification, like planarity and linear logic, for example, to find a way to have a more planar graph using planar in a, say, metaphorical way in your sense. You understand what I'm saying? Because also in linear logic, when we try to make, for example, I speak from the point of view of natural language, we try to make diagrams that are proofness in linear logic. For natural language, they were very complex. As soon as the complexity of the context appeared, then we were working. So the solution was to find out these simplified diagrams that are planar. So, and from that groups, for example, were creating this kind of things. I mean, is a similar problem in your approach or not? But with any question, I mean, just because.
I'm not sure. Maybe we could.
Okay.
Okay. So let me just fire up the tool. So this is quanto-derived. You see what we've got along here are various folders on the left. I've already got a project open, which is the sample project you can download and play with. And the first thing you might want to do with this is create a graph. Alright, so I've got a graph here. And add some nodes. Let's see. I can add some boundaries, which are these are sort of dummy nodes. They let you hold the kind of input and output wires. Right? So here I've created a very simple graph. And I might also want to create rewrite rules. So create a new rule like this, and say one of the strong complementarity rules was a copy rule. So I'll create something that copies a node. Put this a name. Something like copy. Right. Now I can use this rule. Let's make this graph a bit more interesting. Don't worry, I'm almost done drawing, so I'll let me draw for a moment. So I've made a slightly more interesting graph here, and I say start derivation. And I add this rule that I just created, right there, called demo copy. And immediately it starts searching for ways that this rule applies. And it applies to certain things that I select. So here it doesn't apply at all, here it doesn't apply at all, but here it applies in two different ways, because it's symmetric, right? So I can look at the ways that it applies. If I want to be a real perfectionist, I can sort of straighten things a bit. And I can apply the rule, right? And then, well, it turns out this rule applies again, so I can apply it again. Right? And now, when I'm done, rather than just getting the graph that I ended up with, I get a derivation. So something that I can roll back through and see what happened to this graph. Right? So here, I see that a rule has happened here, and a rule has happened there, and a rule has happened there. Right? And this derivation sort of constitutes a theorem that I've proved in the language. Right? So give this thing a name, because theorems want to know where they came from. So I'll call you demo copy again. And I'll export this thing as a theorem. I'll call you demo, say, read copy. Right? Now if I take this graph again and I start a new derivation, then I'll have that theorem sitting around, and I can use it. I can use it right away to get my free copy to happen. Right? But one of the other things you can do in derive is you can sort of explore, you know, the search space here of what your derivation is doing. Maybe I'll just add a bunch of rules. So you can add as many rules as you want, and it's looking for all the ones that apply. Kind of in parallel. So if I look at what applies here, I should get a red spider. See? So these two red nodes will merge using the spider fusion law. I can apply that rule and see what happens. It creates a new branch. So it's saying, actually I'm trying something else now. Maybe this didn't go so well. I'm trying something else. And in fact, if I want to give up on this, I'll just say, I don't want that branch anymore. Alright, so now I've applied that. But now if I look at my demo copy, of course it doesn't apply anymore, because I made a stupid choice of how to apply these rules. And in fact, it turns out that I need something that copies 3 outputs, or maybe, you know, k outputs. That would be a much better rule than this quite simple one. So we can do that. The way we do that is with these bang boxes that were on my last slide. So what this rule means is a red with k outputs will create k greens. So I'll save that. Something like demo k copy. Right. And I'll come back to my right here at the bottom, yeah, and I found something, so apply. And that'll happen for n. Right? So you can create some quite sophisticated looking rules using this kind of setup. For instance, this rule will take a connected bipartite graph and change it into a cotree followed by a tree, right, which is a generalization of the bialgebra law, which you can prove is true in the ZX calculus. So that's what applying single rules looks like. Let's get to something a bit more heavy duty. So I'll take this rule, or this graph, which I'm sure Peter won't recognize, but I lifted this from his paper about normalizing Clifford circuits and translated it into ZX calculus. This is the biggest rule in his sufficient set of rules, and I wanted to prove that they were all correct. So I'll start a derivation here, and rather than doing single rewrites, which I could start doing, I'll simplify this, or try to simplify this. Now the way Quanto does simplifications is with simplification procedures. So these are little bits of ML code, but actually the naive ones, you don't really need to know ML. Here I've just loaded up a list of rules, and I've registered this procedure to say, keep applying rules until I can't apply rules anymore. That's what this reduce all simps means, and basic simp is what I've decided to call it. So I'll load that thing, and we'll see how good our naive procedure does. Not very good, right? Because, well, this stuff is tricky, and it's choked on that, right? But there's actually a much, much better way you can simplify these red-green graphs, which we've only discovered recently, which is called rotate, or rotation simplification. Now this actually uses something to do with this kind of vector space semantics for these diagrams, but I won't go into that. But this gives you an example of a non-trivial way you can write a strategy. So this is saying, do this for a while until I can't do that anymore. And then do this as long as you're decreasing the value of this function, right? This is a function from graphs to the natural numbers. And then keep looping, doing similar things in here. And then once all this stuff dies, then you do this until I can't do it anymore, and then I'm done. Right? So this is a much more non-trivial strategy, which if you've ever written tactics in a theorem prover, they look a lot like this. So, where is that guy? Let's load that up, and we'll see how that does. Much, much better. So, and in fact, if you look at what this thing simplifies to, it is a swap of the first two key bits. I mean, if that's, I don't know why that's true anymore, of course. These things are quite big. But as you can see, what was done is still here, right? It's a bit messy. I could go back and clean it up if I want. It did its best to make it look nice. But what Quanto is something that's not really just about doing these kinds of derivations, but also about kind of communicating them once you have them done. And the way we communicate is with papers, right? So the kind of cool practical thing this does is LaTeX export. So here I've got a paper, and right now there's some placeholders for a figure. Theorem 1 is there, and its proof is going to be by simplification, right? And that I can pretend like I came up with this great proof, but actually Quanto did it for me. So let's see. Let me save this derivation. I'll call you demo, say, sim. And let me export the theorem that comes with it. So this is a theorem. I'll call you, say, demo 3 gates. Let's have a look at that theorem that came out. Yeah, that looks like the thing that I just proved. export that guy. Now I've got to call this thing the right thing, or this is all going to go wrong. I think that's called sample. Now if I come back to my my PDF, make some little change to it, build it. Okay, there's my rule showing up there. Now if I go over to, where did I put you? There? Yeah. Let's export this guy. Sample proof, it's called. Now let's see if that. Okay. So, yeah, that's a day's work done in about 3 minutes. Yeah.
Can it also referee papers?
Oh. 2.0. Yeah, so that's.
But there's a serious point there, right? I mean, if you're submitting this to be published, that's not machine readable, right?
Right. Yeah.
What
So.
you're submitting is the, I mean, it is, you know, the set of rules you're using and the logical definitions of these proofs, which should then be machine checkable by the referee.
Right. Yeah. So there is some of that in the theorem proving community where you have these literate proof documents which you can send to people.
And
So-
there's a multi-type theory community, right? Lots of various
Right. Yeah.
types.
Yeah. So really, you should attach this when you send your submission, right? This project file.
A lot of people write papers in Isabel these days.
Right. Just use the kind of pretty printing kind of feature, or the.
I don't know how to do it.
There's a way that the whole thing goes to LaTeX, I think, as well. So, yeah, we're drawing a bit of inspiration from some of those techniques here. And of course, the concerns are a bit different because it's all graphical. But unlike most of these really researchy things where it's a real arduous procedure to get this and play with it yourself, just go to this website and get it on your whatever your computer happens to be running, and it should just double click and go. If it doesn't, pop us an email, and we'll try to sort that out for you. There's a bit of a tutorial here. In particular, this sample project that I've been going through is here as well, so you can download that and start playing with it. So yeah, I'd be really interested to see how people might like to use this and what they think. So, thanks.
Any questions, comments?
And what language did you write?
So, Quanto Core, which is the rewriting the engine library, is written in ML. The front end is Scala.
Any more?
So we saw in the first half of your talk that the kind of graphical language illuminates kind of the structure of these quantum algorithms, and I was kind of wondering, is there a way that this kind of intuition diagrams can give you more kind of general algorithms that work better than some of the old ones, or just a new kind of like way of going about deriving quantum algorithms, or thinking or reasoning about them, or coming up with them in the first place?
So you guys were working on generalizing Deutsch-Jose, right? Did you get much traction? I'm looking at you. Yeah, I'm delegating here.
Yeah.
Yes.
What's the question?
I guess Jamie wasn't Jamie.
I guess the question was just, is the kind of this graphical language and the intuition line of rewriting diagrams, does that give you a new way to kind of come up with algorithms, or does it give you a new intuition for how to kind of come up with a quantum algorithms? Because all the algorithms have that same kind of structure.
So I think something that happens quite often is it shows you what the high level structure of the algorithm is, which makes it then a lot easier to generalize the algorithm. Right, and with these algorithms that Alex described earlier, with the high level structure, the low-level structure is here's just a bunch of matrices that multiply together. High-level structure is some group theory going on. And then the observation is, well, what if I didn't use this group, what if I use another group? It'd be totally unclear that that made any sense with the ordinary representation. But high-level representation makes total sense, and then you instantly get new generalizations, and the proofs of correctness just all go through a chain and so on. So that happens. That general way of let's give you something new, give you something more general, which obviously newer sense.
Any more questions? Logan?
Yeah, just a small remark. We forgot to update the download links, so they currently are pointing to the older release.
Okay.
I mean on the website, but you can download it from the GitHub website.
Yeah. Or wait an hour before
Yeah.
clicking on the download link. That's a good point.
Okay, so we thank Alex and